our today's guest is Niklas. He's a research engineer at Contextual AI. He'll be starting his PhD at Stanford. He has worked on so many interesting projects like the Bloom Z, StarCoder, Octopug, and even Aya. So Niklas, welcome, and you can get started.
Thanks so much for having me. So I'll talk about scaling data constraint language models, which is a work jointly done with amazing collaborators. And on a high level, we'll start by looking at how do we scale language models in general, just a quick background on what is scaling, why we're scaling them, and how do we scale them. And then in the second part, we'll go into data constraint scaling, specifically scaling with repeated data and mixing data sets and changing existing filtering strategies. And feel free to just jump in with questions, interrupt me anytime. I think you can just unmute, and then we can discuss. And we can also take more questions at the end. All right. So on a high level, what is scaling? There's two big ingredients, which is the model size and measured in parameters, and the training data measured in tokens. And together, they make up the training compute. So over the past few years, we've gradually scaled up from models like BERT in 2018 with only roughly 100 million parameters and 250 billion training tokens, which constituted this compute budget. And then 2 years later, GPT-3 had a few orders of magnitude more parameters, also more training data, and thus a larger compute budget. And then we went even further in 2022 with PaLM, again, scaled up both in terms of parameters and in terms of tokens. And so why have we kept up scaling over these past years? The reason scaling is important is that we've observed as we keep scaling up these models across these axes, model size, training data, and thus compute, performance as measured in test loss here on the y-axis keeps getting better. So it keeps getting, loss keeps decreasing, which means better performance. And specifically, they improve as a power law with this increase in model size, training data, and thus compute. Now, how should we scale? So we've established that there's good returns from scaling, and scaling is really important. But how should we scale? How should we allocate our compute budget to these axes of model size versus training data? And then in this work from Chinchilla, they show that they should be scaled equally. So here on the y-axis is the model size measured in number of parameters, and on the x-axis is the training data measured in tokens. And the gray line demonstrates the optimal scaling, which means equal increase of both. And then they show that with their model, this Chinchilla model, which is the blue star, they were able to get better performance than the other models depicted there by equally scaling. And further in that paper, Chinchilla, they put forth a predictive formula to estimate loss given those two inputs, the model size and the training data, in addition to a bunch of learned constants. So in this formula here, A, B, alpha, beta, and E, they're just learned, and you input N and D, and then you're able to predict the loss. And when they fit this formula, they find that alpha is roughly equal to beta, which corresponds to an equal scaling of N and D. Now, the problem is that while the number of parameters is something that you just set in your code, the data has to be acquired externally usually. And the amount of data that is available is constrained. So here's a plot from prior work where they estimate that given this trend of spending more and more compute along parameters and data, they estimated that in 2024, high-quality language data, according to their definition of it, will be exhausted. And when we talk about high-quality language data, it's things like papers, of which there's roughly 1 trillion tokens on the internet. There's books, a bit more of those, and some other sources like Wikipedia and some other high-quality websites. But overall, there's not a lot. There's also code data. However, it's been unclear how useful that is exactly. And then for low resource languages, we are already hardcore data constrained. For example, in a follow-up project working on Finnish, we were only able to get 38 billion tokens across both public and some closed sources we had access to, like libraries and so on. And this is not enough to train a really large and good language model. So we already are data constrained in many scenarios. So now we'll go into how do we deal with these data constraints. The first very simple idea is, okay, we are data constrained. Why don't we just repeat the existing data? However, when we started working on this, repeating data was considered harmful for large language models. Specifically, in the GPT-3 paper, they write that data is sampled without replacement during training. And in PaLM, they explicitly state that they avoid repeating data in any subcomponent. And there was some additional work that said you should always train for one epoch and you shouldn't repeat, and so on. So we asked, is it really that bad? And try to investigate this empirically. To do so, we set up these 3 different configurations with 3 different flop budgets, so 9.3, E20, and so on, increasing number of flops. And those flops are, again, allocated across those 2 axes of model size and training data. Specifically, for the first one, 2.8 billion parameters trained for 55 billion tokens, and so on. And these setups, we just pick them such that they're compute optimal, such that they're expected to give the best performance according to the chinchilla scaling laws that we saw earlier. And for each of those setups, we vary the amount of those tokens that are actually unique. So we might have one setup where the full 55 billion is unique, and then one where only 28 billion are unique, and they have to repeat it twice, i.e. for 2 epochs, and then to reach the full compute budget. And in addition to those baselines, we have like roughly 300 various other runs. And across all runs, we use very common presets, like the GPT-2 architecture, hyperparameters from Chinchilla, and very commonly used datasets like C4 to ensure that these findings will be broadly applicable. So now let's take a look at how these experiments turned out. On the y-axis here is validation loss, so the lower the better. And then on the x-axis is the number of training tokens. And we have our 3 setups here, so from 2.8 billion parameters up to 8.7. Let's add in the first run. So this run here is just the default, where we train for a single epoch, as used to be common for large language models. And as expected, the loss goes down as we train for more tokens and the model gets better. Now, what happens if we train for 2 epochs? Interestingly, the loss curve for 2 epochs is very similar. So here, for the setup on the left, 28 billion tokens are unique, and they have to repeat it twice to reach the full token budget or the full compute budget. And even for 3, 4, 5 epochs, it still looks very similar. However, eventually, as less and less of the data is unique, we do see it diverging. And at 44 epochs, it completely diverges. So here, only 1/44 of the data is unique, right? So for the setup on the very left, that's like a bit more than 1 billion tokens, so not a lot. However, for very few repeats, we do see very similar performance. And this suggests that we can scale a lot further with existing data constraints, simply by repeating data. Now, can we be more principled and try to predict how much we want to repeat? Our hypothesis is that data repeating behaves similarly to exponential decay. Intuitively, when you repeat data, it isn't worth as much anymore as the first time you see it. But there's still some value in it because you haven't learned all of it the first time you saw it. So some fraction of its original value is lost, some fraction delta, but a bit remains. And this is similar to exponential decay, where sort of at each step, for example, here, the atom kind of decays and there's less and less of it. And it's relative to its prior weight in this case. So to do that, we define three factors here. So we have a d prime, which is the value of our total data. U is our unique data. So this is the unique data we have and that we have to repeat for rd number of repetitions. And we can express this with a simple formula where the value of our total data is the unique data. So the sum of the unique data at each repetition. So for the first repetition, it's just u, and then plus 1 minus delta times u. So it has lost some of its value, but it still has some value. So this is represented by this 1 minus delta factor. and so on and so on. And we do this for RD number of times. And here, in the extreme case, where delta equals 1, then all the 1 minus delta, they just cancel out, and we just get, so all of them just become 0, right? And we only left with the first u if delta is 1. So that means that repeated data is worth nothing. On the other side, if delta is 0, then we get u plus u, right? So the 1 minus delta just becomes 1, and so on. And it's as if repeated data is as good as new data, right? So if either one of those is true, then this formula can accurately represent those. However, as we've seen from the prior experiments, it's likely somewhere in the middle, right? It's not as good as new data, but it's also not worth nothing. So maybe something like 0.5, where it retains 50% of its prior value at each repeat. But we like to find this value empirically. We further simplify this formula a bit with this approximation down here. It's essentially the same thing. We just add in this RD star instead of delta, which is our learned parameter, and it represents the number of times that you can repeat before you see sharply diminishing returns. And similar to above, you can look at different values of RD star, one being repeated data being worth nothing, and the other one repeated data being as good as new data. All right. So now we've looked at how this formula looks like, and now we're going to try to use it to predict loss. Here on the left side, we're plotting the final test loss on the y-axis. So this is, again, our performance. The lower, the better. And on the x-axis is the fraction of training tokens that are unique. So on the very left, at 100%, nothing. We don't have to repeat anything. We have 100% of our data is unique. At 50%, half of it is unique, and it has to be repeated twice, and so on. And here's, again, our first setup. So 2.8 billion parameters trained for 55 billion tokens. And now the dashed line that goes up diagonally corresponds to assuming that we stop training when we exhaust all unique data. So essentially, unique data is worth nothing, and we just stop training when we would have to repeat. And the dashed line that's just horizontal corresponds to assuming that repeated data is worth the same as new data, right? So regardless, if only 25% of our training tokens are unique, we still get the same final test loss. And again, our empirical dots here, so each dot is one model that we train, they're somewhere in the middle, right? It goes slightly up, so performance gets slightly worse as we have less and less tokens that are unique, but it's still worth something. And the solid line represents the prediction made by our data constraint scaling loss. So by this formula that we just looked at, which we fitted on tons of samples. Here's the same for 4.2 billion parameters. Again, the formula matches fairly closely with the empirical dots. And then for 8.7 billion parameters. Interestingly, it seems like for 8.7 billion parameters, the fit is the best. So there might be something like where as we go bigger, the fit matches slightly better because there's possibly less randomness, or it's more, our fit kind of scales better as we scale up the model. And now on the right side, we will use this formula to predict loss if we're training for trillions of tokens. So let's take this formula and extrapolate it further. So here, the first setup is, again, 2.8 billion parameters. And the solid line is the predictions according to our fit, whereas the dotted line is if we, again, assume that repeated data is worth as new data, which is the same as saying we just have infinite data. We're not data constrained. And while we see that for a few epochs, they pretty much overlap. At one epoch, of course, they exactly overlap up to one epoch since we're not repeating there. And then at 4 epochs, they're still very close. And then eventually at 8 epochs, they start to diverge. And eventually, the solid line flattens out. So what this tells us is that while we do get a lot of benefit from repeating for a few epochs, in the limit, those returns will diminish to 0, and repeating will not add any value anymore, which corresponds to this curve just flattening out. We can't improve test loss anymore. And then here the same for 4.2 and 8.7. And as said, across all those setups, repeating for 4 epochs is pretty much as good as new data, which is seen in the dotted line and the solid line overlapping, more or less. Yeah, and what's also interesting to mention here is that across the sharply diminishing returns, they really kick in at 16 EP. And this is precisely the value that we got for RD star. So you recall earlier, RD star represents the value of repetitions where we start seeing strongly diminishing returns. And we also see this visually here. I want to go quickly back on the formula and how we used it for these plots. So here's again the formula from Chinchilla, which again, N is the number of parameters and D is the number of tokens we're training for, and all the rest is just fitted constants. And we use this formula that we discussed, this exponential decay formula, to estimate the value of our total data. And then we just replace the existing D in the Chinchilla formula with this estimate of the value of the total data. So UD here again is the unique data, and RD star is this parameter that we fit that corresponds to how many repetitions we can do before we see sharply diminishing returns. And RD without the star is the actual number of repetitions. And we do the same for the number of parameters, N. So we take a similar version of that formula, just using N instead of D, and also replace the number of parameters, N, in the Chinchilla formula. And the intuition here is, well, maybe first, the way this formula works is Rn star is, again, a fitted value, which corresponds to roughly how many times you can repeat your optimal parameter allocation before you see sharply diminishing returns and adding more parameters or repeating parameters. And Rn then corresponds to the number of those parameter repetitions. And the unique number of parameters, Un, similar to the unique number of tokens, corresponds to what's written down here, Un equals min n opt n. So it's just the minimum of either the optimal number of parameters given the number of unique tokens that we're trained for, or the actual number of parameters. So essentially, UN is the optimal number of parameters that we would use if we have a given number of unique training tokens. And then if we add parameters beyond that, we exponentially decay their value. Right? It's similar to repeating parameters in a sense, where if we add far more parameters than what is optimal, given the unique training data that we have, then those parameters will end up learning the same features as the optimal number of parameters. So in some sense, they're kind of repeating information and they're repeated parameters. And therefore, we also decay the value of adding these repetitive parameters. So now we fit this new formula on 200 training runs in order to learn these two parameters, RD star and Rn star. So RD star corresponding to how quickly additional repeating data decays, and Rn star how quickly repeating parameters decays. And from our fit, we get that RD star equals 15.4. So this corresponds to a delta of 0.06. So delta was the formula we used earlier. And Rn star equals 5.3. And that's a delta of 0.19. So intuitively, these values mean that since Rn star is smaller than Rd star, we get less benefit from repeating parameters than repeating data. Or in other words, since the delta for Rn star is higher, 0.19, repeating parameters decays faster than repeating data. So we get less of the value. Yeah, and so the 50.4 precisely means that, as we saw in the plot earlier, roughly around 16 epochs, we start seeing sharply diminishing returns. All right, 15.4, roughly at 16 epochs, we get sharply diminishing returns. And so you have to be very careful if you want to go beyond 16 epochs. All right, If anyone has a question, feel free to jump in anytime. Okay, moving on. A quick reminder here that earlier, the chinchilla results told us that when we're not repeating data, we want to scale model size and training data equally. Now, how does this change when we are repeating data? Do we still want to scale them equally, or is there a change in the way we'd like to allocate our compute? So this is what we try to answer next: allocation, how to scale when repeating. For these experiments, we train on 100 million tokens of unique data, and we vary the model size and the number of repetitions that we do over those 100 million tokens. So here on the left side, we have the number of parameters on the y-axis from 7 million to roughly 7 billion. And on the x-axis is the number of epochs that we do over those 100 million tokens, or the data repetitions. And then each dot corresponds to one model that we train. And the color of the dot, as well as the contour lines, depict the loss or the performance. And the lower, the better. And then we highlight two models here. One is the black star, which corresponds to the compute optimal model for 100 million tokens, trained for just a single epoch. And then the white star is the lowest loss that we're able to get. And we see that by repeating for multiple epochs and training a much larger model than what would be considered compute optimal according to Chinchilla, we get much better loss. Right? We're able to reduce the loss from 8.1 to 3.72. Again, highlighting that there's a lot of benefit in repeating data, and you can get much better models that way. So now, can we predict precisely how those contours look like and how we should allocate? So here on the right-hand side are the predicted contours according to this data constraint scaling law that the formula that we saw earlier. And what you will see is one big difference is that in the contours that are predicted on the right side, they're just curves, while on the left side, they are becoming full circles. The reason for this difference is that empirically on the left side, what we're seeing is that if we go too big in terms of parameters or repetitions, then performance starts decreasing again, right? So the dots, they get darker again, and performance gets worse. For example, with some of these models with like 2.1 billion parameters up in the upper right. And the reason we're seeing this is likely because we're not doing any additional regularization here. So we're not doing any early stopping or something. So we just train the model for the given budget, and then whatever is the final performance is what we take. But in practice, you would, of course, just stop training once it starts getting worse. You would early stop. And so in our formula, we assume that additional repetitions or excess parameters will never actually hurt performance, but only plateau, and you will just early stop, right? So the value of those excess parameters or additional repetitions only decays to 0. It doesn't decay into negative territory, and eventually it'll hurt performance. So I think that's a fair assumption, because in practice, that's what people will do. And if you would have optimal regularization here, then we would not expect models to get worse again as we move to the upper right.
Niklas, I think we got a question.
Yeah, sure.
Yeah, sorry, I'm just going to take advantage. You said jump in, so I will. Thank you for the talk. Very quickly, is this with some kind of learning rate scheduler? That to me seems like the main reason that you might not just be sort of traversing bottom to top, but it would in fact make a difference if you chose ahead of time your total epochs.
Yeah, so we're choosing that ahead of time. We're doing a cosine learning schedule to 10% of the original learning rate. So yeah, it follows a cosine schedule. So yeah, I think that also impacts results. Yeah.
Thank you.
Yeah. It's an interesting point, because it's kind of a pain, because of the schedule, we have to train each model from scratch.
Yeah, you're not just stopping when you're happy, but you actually have to run a different experiment each time.
Yeah, yeah. I mean, I guess you can still early stop. Like you still see the loss during training, and for like we saw in the repeating plot earlier, where it starts going up again, we can just, based on the validation loss, we can still early stop. But yeah, ideally you would know ahead of time exactly how much is optimal. Yeah.
Thank you.
Yeah, good question. All right, and then, so this is the reason for this difference, but otherwise the curves are very similar. Another important observation here is that the contours, the distance between the contours increases as we move to the upper right. And this is because there's diminishing returns to repetitions, right? So as we repeat more and more and move to the upper right, then it's harder to get to that next loss level because we're getting less value out of each repetition. And next, we're going to draw in the efficient frontiers. So here, the dashed black line is the efficient frontier according to chinchilla scaling laws. So this corresponds to equal scaling of parameters and data, so just a diagonal line. And then, according to our efficient frontier, based on these data constraint scaling laws, we find that actually you want to scale data slightly faster than parameters. Thus, it branches off slightly below the chinchilla curve on the right plot. So up to 1 epoch, they exactly overlap, because if your unique data is equal to your total data, then our formula just reduces to chinchilla. It's exactly the same. In a sense, it's a generalization of chinchilla, because as long as you're not repeating, it's the same. But then as you repeat, it is able to account for that those diminishing returns from repeating. And that's why it branches off below here, and then gradually fades away as it gets closer to the white star, because at that level, the returns from repeating have diminished so much that you're not getting any value out of it anymore. And so there's no, you don't want to go further than that. So yeah, again, written out here, hypothetical equal scaling chinchilla, and then our formula says scaling data faster than parameters when repeating. And the reason it branches off below chinchilla and not above is, again, because our fit showed that RD star is bigger than RN star. In other words, the repeated parameters lose their value faster than repeated data. Thus, we want to lean a bit more toward repeating data rather than adding excess parameters. If RD star and RN star would be equal, then it would just overlap with chinchilla, right? And if RN star would be bigger than RD star, in other words, data repetitions would lose their value faster than repeating parameters or excess parameters, then it would branch off above. Great. And so this was 100 million unique tokens and relatively few parameters, I think up to 7 billion. Can we test this at larger scale? So here on the y-axis, again, is the number of parameters. And on the x-axis, we have the tokens and the epochs written below. And we trained 2 models here. One is allocated according to equal scaling, assuming that even for multiple epochs, we want to scale equally, which is this black line, and then the corresponding orange star that lies on the black line. And the other model is allocated according to our fit, which means scaling data faster than parameters. And that's this gradient line with the red star on it, slightly below. And both of those models, the orange star and the red star, they use the same total compute, so both 10 to the power of 22 flops. They only differ in their allocation to parameters versus tokens, right? So the red star, slightly less parameters and more tokens, which also means more epochs, whereas the orange star, less tokens and less parameters. And both of them have the same number of unique data. So both of them have 25 billion unique tokens, and we repeat them for different amounts. And it confirms that the red star, which is allocated according to our fit, given the same constraints, performs better than the orange star with slightly lower loss. So loss of 2.359 versus 2.376. And this might seem like a small difference, but it's actually fairly meaningful at these scales. But let's also take a look at downstream performance. So here's the chinchilla model on the left side, 8.7 billion parameters and 7 epochs, which is the suboptimal one. And we measure downstream performance on very commonly used NLP tasks like HelloSwag, Story Close, and so on. 16 in total, 19 in total, so 16 others. And the data constraint one on the right side, again, measured on those same downstream tasks, it gets better performance across the board and a better average score. And here we also average across 0 to 5 few shots. So lots of scores that are summarized here. And we find that it is consistently better. All right, so this was repeating. If there are no questions at this point, then we'll go into complementary strategies to solve data constraints. The first one we're going to look at is filling with code. So the idea here is simple. We are running out of our high-quality language data from Wikipedia and so on. Let's just add all of those trillions of tokens from GitHub that we saw early on. How good are they? And then the other idea is, can we revise existing filtering strategies? So one reason why we're often data constrained is because we're losing a lot of data from some filtering strategies. So we reinvestigate how valuable they are in the context of repeating and data constraints. Great. So here we train 97 models, each for 2.1 E21 flops. So these are models with roughly 4.2 billion parameters and trained for 84 billion tokens, so fairly large scale. On the y-axis, we have the average performance across 19 NLP tasks, so the same downstream tasks that we discussed earlier. And on the x-axis is the data budget. So if we're at the very left where the data budget is 100%, we don't have to use any strategy. We have enough data, so we don't need to repeat or fill with code. But as we go to the right, we have less and less data available. So we need to do something to reach the full compute budget, repeating or filling with code and so on. Let's start with repeating. So we already got the intuition for repeating. Here in the purple line, again, depicts what happens in downstream performance. So at 100%, our baseline, we're not repeating at all. We get roughly 22% average score on these 19 tasks. And as we go to the right, and we have to repeat more and more, the average score, average downstream performance stays roughly the same, right? The purple line stays roughly at the same level, up to, say, 25%, maybe a little bit more. And then it starts going down quite quickly. So 25%, again, corresponds to 4 epochs, right? So we have 25% of our data available. We have to repeat it 4 times to reach the full 100%. And again, in line with the plots that we saw earlier, at around 4 epochs, the performance of repeating versus having just as much unique data is pretty much, the difference is, there's pretty much no difference. And that's what we also see here in terms of downstream performance. But yeah, if we go, if you have too many repetitions, then performance does start to decline. And then we look at let's look at the red line. So this corresponds to filling missing data with Python code from GitHub. So we're running out of data, and then we just use code from GitHub to make up for that. And again, it starts at the same baseline on the left side, since at that point, we're, again, with 100% of our language data, we don't need to use any Python code. And then as we go to the right, the red line, interestingly, also stays at roughly the same level. So within the shade here corresponds to the standard deviation across 5 seeds. So for each dot, for each empirical dot, which is one of those 4.2 billion parameter models, we train 5 seeds and then visualize the standard deviation. And yeah, it stays within the standard deviation of also the purple line, more or less. But then eventually at around 25%, a bit more, it also starts to decline. So at 10%, it's pretty obviously better than pretty obviously worse where it was at the beginning. And so here, 10%, we have 10% of our language data, and then we need to add in 90% of Python code. So the bulk of the data is now Python code, even though the tasks we benchmark on, which is the y-axis, they're all natural language tasks. So those are not coding tasks, right? If we would be benchmarking coding tasks, then it would probably look very differently. But this suggests that Python code, or code in general, likely also allows us to solve existing data constraints and helps with language performance. In particular, what's interesting with these experiments is that we see that some of those natural language tasks, they spike as soon as we add Python code. So there's one task in that mix, which is called Babi, which is about keeping track of states as people move around like a house. So one person might move from the living room to the kitchen and then somewhere else. And the task is to keep track of where that person is. And if we're not adding code, so we just train on natural language, the performance is consistently 0. But as soon as we add code for the red line, then it goes up. one hypothesis is that code teaches the model to keep track of states, because if you want to predict code well, then you also need to keep track of what each variable is holding at a given point in time. So the model learns keeping track of states, and then it is able to also apply this to this task when we benchmark it. And then there's two stars here, the yellow star, perplexity filtering, then repeating, and the orange star. So for the yellow star, we perform perplexity filtering, which corresponds to training. We train a very small model on Wikipedia. So this is supposed to be a super clean and high quality data set. And then we take this model and run it over our language corpus, our big language corpus, and only take samples from this corpus with a very low perplexity. So where the model has low perplexity, and the intuition is that if this Wikipedia model has low perplexity on these samples, in other words, it can predict them really well, then they're likely very similar to Wikipedia and of very high quality. And so by doing this filtering, we're indeed able to get the best performance on this plot here. So the yellow star is far above all other dots, even though we filter it down so much to 50% that we have to still repeat this clean data twice. And I think the really interesting message here is that you're often better off quality filtering or applying some really good filter and then repeating rather than keeping your big data set. So say you want to train for 2 trillion tokens and you have a 2 trillion token data set. Rather than training on this 2 trillion token data set for one epoch without repeating, you might be better off applying a good high quality filter like perplexity filtering, reducing it to 1 trillion tokens, and then train on these 1 trillion tokens for 2 epochs. Right? So you have the same total compute budget, but the second approach might lead to much better performance because the penalty from repeating, the slight performance drop from repeating is so small that the gain from the quality filtering will completely outweigh it. And this is what we find here with this perplexity filtering. And then for deduplication, we find that it performs badly. So the orange star is lower than most other dots here. And the reason for that is likely that too much deduplication can hurt. So here we're using the C4 dataset for these experiments. And this dataset is already deduplicated. So if we do additional, more fine-grained deduplication on top of it, we're actually hurting the model. And it's too much. So you have to be careful with deduplication, and you don't want to do too much. So yeah, again, going over the key messages here, filling with 60% of code is roughly as good as natural language data on these natural language tasks. And deduplicating clean data sets might not help. Great. So now I'll go through the takeaways. So the first very simple takeaway is that repeating large language model data roughly 4 times is fine. There's diminishing returns, so you don't want to do too much. And it might also, there's some other considerations like what data are you actually using and so on. But sort of as a simple, if you want to make it very simple, then roughly 4 times, 4 epochs. The second takeaway is that 50% code data is fine. So you're running out of data, just double your data with code. And natural language performance will roughly stay the same, plus you maybe get some boost on some coding tasks. So this also allows us to solve data constraints. And then finally, quality filtering plus repeating can be a good strategy. In fact, better than neither of those, than just having a bigger data set and training on that for 1 epoch, as we discussed with the perplexity filtering experiments. And now finally, I want to take a quick look at the impact of this work. It's been really cool to see it have an impact on the community. So it was at the last NERVS conference, got one of the awards. And then here on the right upper side, we, in a follow-up work called FinGPT, we trained Finnish large language models. And as mentioned at the beginning, we were only able to get 38 billion unique tokens. So we just repeated those for 8 epochs based on these findings. And validation loss was very smooth, as seen in these plots, across up to 13 billion parameters. And this allowed us to train actually somewhat useful Finnish large language models, despite the hardcore data constraint for this language. And yeah, various other works have made use of it, which has been super exciting to see. Thanks a lot. I'm happy to take any more questions if there's anything.
That was wonderful. Awesome. I'm sure a lot of you will have questions, so feel free to ask. So friends, you can go ahead and ask. I think your name is Franz, so you can go ahead and ask. I don't know. Okay, so let's go with Nayara then.
Hi, hello. Thank you very much for the talk. So my question is related to double descent. Probably you need to see it, to repeat a lot to see some double descent effect. But have you seen something like this?
Yeah, we have. Let me show you. I have the appendix up here.
Cool.
I can show you directly.
Yeah, because usually we see like a smaller. Oh, I see.
Yeah.
Oh, interesting. Oh, 200 epochs, all the models.
Yeah. So interestingly, yeah, exactly at the same level, they all double descent at 200 epochs. So here the y-axis is loss, and then x-axis is epochs, and those three different models at all at 200 epochs, they go up and then down again. Is very funny.
That's funny indeed, because I'd expect there would be some shift to the right if you're a more complex or more complex model or something like this.
I see. Yeah, it's a good point.
Interesting.
It might change. So all of them are trained for the same number of unique tokens, so 100 million unique tokens. But
okay.
Yeah, so one problem with this is that it does add some noise in our fitting. Like when we fit those scaling laws, this obviously adds some noise, but we still were able to get good fits.
Oh, that's interesting. Thanks.
Yeah, good question. It's also, you actually also see it in the contours. So if we look at the contour here on the left, then here at the roughly 70 million parameter level, it kind of becomes very light white first, which corresponds to lower loss, and then it sort of increases again. So you can also see it in this line here going up and down. Yeah, so I think that's a very interesting phenomenon.
Thank you.
Thanks.
Can you hear me now? Oh, yeah.
Yeah, we can hear you. Yeah.
Cool. Hi, Niklas. Thanks for the presentation. I have a quick question. So regarding your scaling law, so maybe I misunderstood it, but as far as I can tell, you do consider the number of repetitions, but you do not consider the kind of number of unique tokens, right?
The number of unique tokens, so that's UD.
I see. Because I would have imagined that if the kind of number of unique tokens versus the model parameter counts, if that like the kind of comparison becomes super like the difference becomes super large, that you would be in an overfitting regime at some point, right? But you don't seem to have encountered that, I guess.
I guess it's a good point. I guess we do. So like if you repeat for many epochs, then yes, you are overfitting. Yeah, so we are seeing overfitting in various places. So actually I can also pull it up here. So one place where we see overfitting is if we have a very large model and very few parameters. So this is depicted in this plot here. So we have the final test loss on the y-axis, and then the number of parameters on the x-axis. And the empirical loss here, so this is empirical loss is the orange line. As we scale up the parameters, eventually it like goes up a lot. And we only train for a single epoch here on 100 million tokens. Sort of if we're hugely over parameterizing, then the model actually gets worse, even though we're using more compute. So I guess this can possibly explained with or has something to do with overfitting, which was very interesting. And then also we're seeing, of course, overfitting if we train for lots of epochs. The training loss, of course, is better the more epochs we train for. So that's why we always use validation loss in the paper. Yeah, does that answer your question? Am I missing something?
Yeah, it does. And I guess, I mean, the only way to combat this in real life, if you're, let's say, in a fine-tuning scenario, would be to I don't know, freeze layers or use LoRa or something, right?
I see. Yeah, that could be. So in some sense, limiting the expressivity of the model, placing some constraints on it. I think that makes sense. Yeah. Yeah, maybe adding some regularization like dropout or something like that could also help. Yeah, that's a good point.
Okay, cool. Thank you.
Awesome. Mike, you can go ahead.
Hey, thanks, Niklas. I guess you also see overfitting in that banana versus just curves, right? As you increase either parameters or epochs, your loss starts getting worse empirically. I wanted to ask, I saw in the OLMo 1.7 models this sort of similar idea, perhaps inspired by your paper. Yeah, you mentioned in the corner that having a second kind of filter to the good stuff and then do it again improves performance. I wonder what your thoughts are on that as a more continuous process. Presumably, it's not just that stuff is either Wikipedia-like or not. Presumably, that could be weighted choices in, say, a perplexity filtered score versus number of, like, you could sort of super sample according to the perplexity quality. Do you have a kind of thought about turning that two-step thing into a more continuous approach of weighting more repetitions for tokens that you think are better?
Yeah, that's a great point. So I think you're referring to this annealing phase, right? With OLMo 1.7, we first train it for like 2 trillion tokens, I think, and then there's like another 50 billion tokens of the second stage.
On higher quality data. Exactly. It just sounded, that seemed very inspired by your presentation.
Yeah, and we also, for that model, actually, we do some repeating already in the original one, so it's more than one epoch. And I think it's a good point. Hopefully we can make this more principled. Like right now it's a bit hacky, right? You just finish training and then you just do another training with like less tokens. I think where we're going toward would probably be something like you have a weight on a sample-based level. So say like how good, maybe a score or something for each sample, and then you just sample from all samples or all documents according to this weight, right? So naturally, some of them, the best ones will get more repetitions. They'll be sampled more frequently, and the other ones less. And then maybe you still want to combine it somewhat with curriculum learning, where you kind of, maybe the weights kind of change during training. Like in the beginning, maybe it's more like the weights are more random because it doesn't matter too much. If you're really like high quality data in the beginning, doesn't really matter because the model, like it's literally random at the beginning of the parameters, so they're hardly learning anything. But then toward the end, maybe you want to increase the weights of the higher quality data and sort of make it a more, as you said, like a continuous thing where you don't like do a two-stage or three-stage thing. Yeah, something like that. Does that make sense? What do you think?
Yeah, totally. I'm an astronomer, so kind of tinkering in a kind of fine-tuning downstream context where people often want to, for example, improve performance on a specific set of archive papers.
Okay.
There's a kind of high-level silliness that the model has already been repeated on all of those papers.
Yeah.
And then there's this two-step thing now, and I'm kind of thinking about how to smooth that out kind of all the way to the end. So yeah, thank you for that. I might catch up with you offline about it.
Yeah, of course. That's so cool. Can I ask, how are large language models useful for astronomy, if they are?
Mostly they're useful in funding astronomers currently. People get very excited and it gives them a reason to do stuff. But I think that there's a few briefly. They're useful for sort of paper search, as with every other field, right? With things like hypothesis generation. They're useful for writing proposals. They're useful for understanding our kind of hacky astronomer code, which is often in our weird languages or poorly written. And I work with citizen scientists, so people will write in natural language descriptions of galaxies, and then there's a step to try to turn that into some sort of higher level science measurements that we're exploring. So that's a quick one.
Awesome. Maybe until then I can ask my question. So what were like the trade-offs in making the decision behind like allocating resources to like more epochs versus like more parameters?
Yeah, so I think the first constraint is so there's two constraints. One is the compute budget, how much flops do you have available? And then the second one is how much unique data do you have? And then according to those constraints, you want to allocate your resources. So if you have infinite unique data, then and maybe a third constraint is how much are you going to use the model at inference? So how much do you care about just performance after training versus also making the model cheap? So let's say you have infinite unique data and you only care about performance after training. then you just go with chinchilla, right? You just allocate optimally according to chinchilla. But now let's say you have infinite compute, but a limited data budget of say some billions of tokens. Then you want to allocate according to our data constraint scaling laws and just train at the very edge here where the line starts to fade away. So just go for as many epochs as you can before it starts to completely flatten out and you don't get any benefit anymore. But both of those scenarios are pretty unrealistic. And in reality, it's something like you have a limited compute budget and you have a limited, you don't have as much data available. And then also, usually you don't just care about performance after training, but you also want to make the model cheap after training, which means that you want ideally few parameters so you can serve it cheaply and a bit more tokens. So in that scenario, you probably want to do something like go even lower than our efficient frontier, right? And be somewhere down here where you're training an even smaller model for more tokens. So say maybe like this one here is like 9.7 epochs, maybe like 12 epochs or something, even smaller. And then also use that very cheap late inference. One example of that, I think, of the models here. So for example, so many of these models, they're already doing things like this. So Llama 3, obviously, they trained for 15 trillion total tokens. So in order to make it for the 7 billion model, which is way over allocated to data, in order to make it very cheap to use at inference. And then also repeated parts of that. And then also for StarCoder 2, for example, they also trained for 4 epochs, despite and the total of 4 trillion tokens, despite the model only having 15 billion parameters. So yeah, those are some examples of allocations. And overall, yeah, I would look at those 3 axes and think about how important they are for you. Does that make sense? Let me know.
Yeah, totally, yeah. Maybe one other question. It might be an open-ended, but I don't know if you have explored this, but does it repeat the same results for, let's say, if I want to train it for non-English tasks, let's say another language that's low resource, using just like 2-3 billion tokens, using the filterings and like 50% of the code, will it repeat the same result?
Yeah, it's a good point. As to, I guess the broader question is how do these findings generalize to settings like that and various other settings? We tried to make it as generally applicable as possible by using like these very basic configurations of GPT-2 transformer, chinchilla hyperparameters, and basic data sets like C4, and did verify it on 2 data sets. So this was C4, but we also results for Oscar, which is another data set where we find pretty much the same curves as we saw earlier. And then we already saw the findings translate to things like these Finnish large language models, but there's still an open question whether it translates to all scenarios. And yeah, like you mentioned, like maybe for hardcore low resource languages, this might be slightly different. I think one interesting axis is also the difficulty of your data. I imagine that the more difficult your data is, the more epochs you can do over it, because the value decays even less because the model is only able to learn less from this very difficult data. So this might have something to do. If you have like a very, very difficult language, then you might be able to do more epochs to get the same value. And then of course other settings like the optimizer, other hyperparameters might also make a difference. So maybe part of the reason why the model is not able to get the full value at each repeat is because the learning algorithm is poor. So maybe if you have a better learning algorithm, a better optimizer than just Adam, which is pretty much used for almost all large language models, and we're also using in this paper, then maybe you actually want to do less repetitions because now you're getting more value or something like that.
Perfect. I don't see hands, so I might also ask my last one. So the double descent graph that you showed earlier on, so is there like a way to determine like the optimal number of epochs to avoid the initial increases in loss?
Yeah, that would be cool follow-up work. I'm not. Yeah. So if you just look at these, then it's always 200 epochs. So you can kind of determine it here empirically based on these three setups. But yeah, it probably varies depending on like the number of unique tokens you actually have and so on. It'd be very interesting to try to predict this. Maybe in the original double descent paper, maybe they have some predictive setup. I'm not sure. But yeah, I think this would be interesting to know.
Perfect. Let me know if you guys have any questions, so you can type them in the chat, or like feel free to unmute yourself and ask. So we have a few minutes.
We've got a question in the chat by Amy Pajak, so I'll just read it out. Does training on all data and then again on higher quality data subset produce a better generalist model, or does it improve the performance to, or does it improve performance to further fine-tune the model?
Oh, if you train on low quality data first and then high quality data?
Yes. Okay, so the question is, if you train it on all data and then again on higher quality data, yes, as compared to further, if you further fine-tune the model, which one, does it improve? Yeah.
So you train it on all data first and then again on the high quality subset, versus you just keep training it on all data, or you fine-tune it on something else?
Versus fine-tuning the model.
Okay, fine-tuning on like instruction data or something like that?
Okay, I'm not quite sure because I'm reading from the chat, so, but I don't know if she's around.
Maybe I guess I can try to at least point to the OLMo experiments, which we briefly discussed before. So in that case, like someone mentioned, they so it's the full data first, and then again a high quality subset, and that showed pretty good performance. And I'm not 100% sure if those experiments are out yet, but I think we are running a comparison of this OLMo model with the second annealing phase versus just taking the model after the first phase and directly doing instruction fine-tuning on it. So do you still need this second high quality data phase if you are doing instruction tuning afterward anyways? I'm not sure if that's out yet, but otherwise it will probably be out soon. And maybe that will answer your question.
Awesome. We are at time, so I will just entertain one last question if you have any. If we don't, yeah, France, you can go ahead.
Sorry. Yeah, I have one more question related to your last set of experiments that you mentioned. So with those experiments, did you like stop early in your cosine schedule and then continue with the instruction fine-tuning?
You mean the OLMo experiments?
Exactly, yeah.
Oh, I see. Yeah, for those, so we set a cosine schedule. So the OLMo 1.77 billion model is trained for 2 trillion tokens, and then after those 2 trillion tokens, there's a second phase of 50 billion tokens. So the model is open source, and all those the logs and everything also open source, so people can look at the training progress themselves if they're interested. And the cosine schedule is, I'm not sure if it's set for the 2 trillion tokens or if we actually set it for much longer, but then just finished it earlier. It's also open source, so you can probably check it on the website. And then what we do for this annealing phase is we just fix the learning rate at wherever it finished from the first phase. So say the first phase, it decayed all the way to like 1e minus 5 or something, and then the annealing phase will just be fixed. We'll just fix it at this 1e minus 5 for those extra 50 billion tokens, and then train at that, and then do instruction tuning again after this annealing phase. Yeah, and the experiments, whether instruction tuning after this annealing phase versus instruction tuning just after the first phase, is still better. So definitely the model after the annealing phase is much better, like especially MMOU increases a lot. But whether it's still better after instruction tuning is still, I think, an open question we haven't looked into yet, but we'll probably very soon.
Okay, cool. Thank you.
All right, awesome. So thank you, Niklas, and thanks everybody for joining us. Hopefully this will not be your last presentation. So feel free to present all your awesome papers. Yeah. Oh, here's the presentation in the chat if you guys want it.
Yeah. So
we'll have the recordings ready in a few days, and we'll share it with you guys.
Amazing. Thanks so much for having me.
All right. Bye, everybody.